The universe is a vast and mysterious place, filled with countless wonders and phenomena that continue to baffle and intrigue scientists and astronomers alike. It is full of wonders that we are only beginning to understand, and each discovery opens up new questions and avenues for exploration. One of these wonders is the phenomenon of fast radio bursts, or FRBs, which have captivated the scientific community since their discovery. FRBs are brief, intense pulses of radio waves that originate from distant galaxies, often lasting only a few milliseconds but packing an incredible amount of energy. They are one of the most enigmatic phenomena in astrophysics today, challenging our understanding of the universe and the forces at play within it. FRBs were first discovered in 2007, when a burst was detected by astronomers using the Parkes radio telescope in Australia. Since then, astronomers have detected hundreds of these bursts, each one adding a piece to the puzzle but also raising new questions. However, their origin and nature have remained a mystery, with theories ranging from neutron stars to black holes and even extraterrestrial civilizations. What could possibly generate such powerful bursts of energy in such a short amount of time? The answer to this question could unlock new understanding of the cosmos. The discovery of FRB 2022-1022. A is a major breakthrough in our understanding of these cosmic events, providing new insights and data. This burst is the most powerful ever detected, with an energy output that has astonished scientists and opened up new possibilities for research. It has provided us with new clues about the origins of FRBs, suggesting that they may be linked to highly magnetized neutron stars, known as magnetars. FRB 2022-1022A was discovered on October 22, 2022, by a team of astronomers using the 500-meter Aperture Spherical Radio Telescope, or FAST, in China, one of the most advanced radio telescopes in the world. The burst was incredibly bright and lasted for only a few milliseconds, yet its impact on our understanding of the universe is profound. Its high brightness and unique properties have allowed astronomers to trace its origin back to a galaxy billions of light-years away, providing a glimpse into the distant past. The discovery of FRB 2022-1022 A is a testament to the power of modern astronomy and the incredible advancements in technology that allow us to explore the universe in unprecedented detail. We are now able to detect and study events that were once hidden from our view, revealing the dynamic and ever-changing nature of the cosmos. By studying FRBs, we can learn more about the extreme environments in which they are produced, such as the intense magnetic fields of magnetars, or the energetic processes surrounding black holes. We can also gain a better understanding of the evolution of the universe from the Big Bang to the present day, and the forces that have shaped its development over billions of years. The discovery of FRB 2022-1022. A was met with great excitement by the astronomical community. This fast radio burst, or FRB, was unlike anything astronomers had seen before. The initial detection was made by a team using a state-of-the-art radio telescope, and the data quickly spread through the scientific community, sparking a wave of interest and investigation. This burst was immediately recognized as being unusual. Unlike typical FRBs, which are already rare and mysterious, FRB 2022-1022, A stood out due to its extraordinary characteristics. It was far brighter than any other FRB ever detected. The intensity of the burst was so high that it challenged existing theories about the energy limits of such cosmic phenomena. Astronomers around the world began to study the burst in more detail. Collaborative efforts were launched involving observatories and research institutions from multiple countries, all aiming to understand the nature of this extraordinary event. They wanted to learn more about its properties and origin. Detailed analysis of the data revealed several intriguing aspects that set this FRB apart from others. One of the most striking features of FRB 2022-1022A is its high degree of polarization. This polarization indicates that the radio waves are aligned in a specific direction, which is not commonly observed in other FRBs. This means that the radio waves that make up the burst are all vibrating in the same direction. Such a high degree of polarization suggests that the burst passed through a highly magnetized environment. This is a strong indication that the burst originated in a region of space with a very strong magnetic field. Such regions are typically associated with extreme cosmic events, such as the vicinity of a neutron star or a black hole. The fact that this burst is so bright and highly polarized suggests that it originated from an extremely energetic event. Events like supernovae or the merging of neutron stars could potentially produce such powerful bursts. Another unusual property of FRB 2022-1022A is its short duration. The burst was incredibly brief, lasting only a few milliseconds. The burst lasted for only a few milliseconds. This fleeting nature makes it challenging to study but also provides clues about the size and nature of its source. This is much shorter than the duration of most other FRBs. The brevity of the burst implies that the source is extremely compact. The short duration of the burst suggests that its source is very small. Astronomers believe it could be a neutron star, which is a type of stellar remnant known for its small size and immense density, perhaps no larger than a few kilometers across. This aligns with the characteristics of neutron stars, which are typically only about 20 kilometers in diameter but contain more mass than the Sun. The combination of these unique properties makes FRB 2022-1022A one of the most intriguing astronomical discoveries in recent years. Its brightness, polarization, and short duration all point to a highly energetic and compact source. It has provided astronomers with a wealth of new data to study. This data is crucial for developing new models and theories about the origins and mechanisms of FRBs. This data could help us to finally unravel the mystery of FRBs. Understanding these bursts could unlock new insights into the most extreme environments in the universe and the fundamental physics governing them. Determining the precise location of FRB 2022-1022A was crucial. Astronomers needed to know where to look for its source. They used a technique called Very Long Baseline Interferometry, or VLBI, to pinpoint its origin. VLBI involves combining data from multiple telescopes that are spread out over a wide area. This creates a virtual telescope with the same resolving power as a single telescope the size of the Earth. By carefully analyzing the arrival times of the burst at different telescopes, astronomers were able to triangulate its position. They traced FRB 2022-1022A back to a dwarf galaxy located billions of light-years away. This discovery was significant. It was the first time that an FRB had been localized to a galaxy of this type. The identification of the host galaxy provided astronomers with valuable information. They could now study the environment in which the burst originated. This could help them to understand the conditions that lead to the formation of FRBs. The discovery that FRB 2022-1022A originated from a dwarf galaxy is significant. This finding opens up new avenues for understanding the origins of fast radio bursts, or FRBs, which are one of the most mysterious phenomena in the universe. Dwarf galaxies are known to host a high number of neutron stars. These small galaxies, despite their size, are incredibly dense with star clusters, making them fertile grounds for the formation of exotic objects. Neutron stars are the collapsed cores of massive stars that have exploded as supernovae. When a star much larger than our Sun reaches the end of its life, it undergoes a cataclysmic explosion, leaving behind a dense core. They are among the densest objects in the universe. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are incredibly small and dense. Despite their small size, they pack a mass greater than that of our Sun into a sphere only about 20 kilometers in diameter. Imagine squeezing the mass of the Sun into an object just a few miles across. This unimaginable density gives neutron stars their unique properties. Magnetars are a special type of neutron star. These rare objects are even more extreme due to their incredibly powerful magnetic fields. They have extremely powerful magnetic fields. These fields are so intense that they can affect the structure of atoms and molecules in their vicinity. These magnetic fields are trillions of times stronger than the magnetic field of Earth. To put it in perspective, if a magnetar were located halfway between the Earth and the Moon, it could wipe the data from all credit cards on Earth. They are so strong that they can distort the shape of atoms. This distortion can lead to unique physical phenomena that we are only beginning to understand. Magnetars are thought to be formed when a neutron star is born with an extremely rapid rotation rate. This rapid rotation, combined with the star's magnetic field, creates the conditions necessary for a magnetar to form. The extreme conditions found in and around neutron stars and magnetars make them prime candidates for the sources of FRBs. These conditions include intense gravitational forces, high-energy radiation, and rapid rotational speeds. The intense gravity, strong magnetic fields, and rapid rotation of these objects can generate powerful bursts of energy. These bursts are capable of traveling across vast distances in space. These bursts could be responsible for the radio waves that we observe as FRBs. Understanding these extreme objects helps us unlock the secrets of the universe and the powerful forces at play within it.